So I want to demonstrate a t-distribution in a single tail or multi-tail, two-tail hypothesis analysis. So in this case, we're going to look at problem 48 from the text. And the problem reads as this. It says, a random survey of 75 death row inmates revealed that a mean length of time on death row is 17.4 years, with a standard deviation of 6.3 years. Conduct a hypothesis test to determine if the population mean time on death row could likely be 15 years. So this is kind of a tricky one. So the first thing I want to do, as always, is just set up my hypothesis statement. So my H sub 0 and my H sub A for alternative hypothesis. So my hypothesis statement in this case is actually this last part of the sentence, that it could be 15 years. So that's the claim, and that's kind of how you have to look at this to interpret this problem correctly. So the claim is that the mean is 15 years. Your argument is that you think that it's actually, you potentially think that it's higher because you did a survey and it came out higher. So the other way you can look at it is you don't think it's 15 years. So let's just go with that second thought of you just don't think it's 15 years. It came out higher for you, but you're not sure. So, but you know that something's off with this calculation. So this is my hypothesis statement that I'm going to go with for this problem. So now let's look at this on a graph. So again, and I actually want to use a different color here, my graph is going to look as it always does with a normal curve. I'm going to have a mean, and in this case we're assuming it's 15. And my argument is actually, what I'm looking for is actually, I'm saying that it's not 15, so it could be on either side. It could be a two-tailed hypothesis. So I think I said single tail in the beginning of this thing, but it's actually we're going to set this up as a two-tail. It could be set up as a single tail as well, but I think it works best as a two-tail. So let's just write down what we're given. What we're given is we are given x bar, which in our case is 17.4. 17.4. We're given the sample standard deviation, S, which is 6.3. We're given the sample size, which is 75. And we're also given mu, which is 15. And we're going to assume a level of confidence here. So we're going to assume a 0.5 level of confidence. So because I know my mu, and I'll just highlight these here. So I know mu, which is here, and but I don't know, what I don't know is sigma. So sigma is unknown. And because of that, I can't use the standard z-score to make my calculation. I actually need to use a t-statistic or t-score to calculate this. So I'm using a t-distribution. I'm using a t-distribution, and therefore I need to calculate t slightly differently than I calculate z-score, but not much different. So our t, if you recall, is going to be x bar minus mu over, and instead of sigma, we're going to use s over the square root of n, where s is our sample standard distribution that's calculated. So if I plug the numbers in here, 17.4 minus 15 over 6.3 over the square root of 75, when you do the math here, you should get 3.3, roughly. So one thing I can do is I can go to table C, and I can look this up. So let me just bring up table C here. So here's table C. I'll try to kind of zoom in a little bit and forgive the highlights, but here's table C. And what you'll notice in table C is that we have degrees of freedom now. We have to look at degrees of freedom when we're looking at a t-distribution. And our degrees of freedom because our sample size is, and I'm just going to highlight it here, is 75, our degrees of freedom are going to be 75 minus 1, which is 74. And now zooming in on this table, sorry, I think I just wrote on the, yeah, so zooming in on this table here, as best we can anyway, you can see there is no 74 on this table. There's a 60 and there's an 80, but there's no 74. So as a result, we're going to kind of err on the side of caution, and we're going to look at 60 degrees of freedom, because the higher you go, the more accurate the more degrees of freedom you have, the more accurate your results are going to be. So we're going to assume less accuracy, because I think that's sort of the right thing to do. So we're going to look at this 60 here. So when we do that, when we look at the 60, we're going to round down, and we're going to follow it down to the two-sided P row. So we're going to look for a number that's close to 3.3 in this row of with degrees of freedom equal to 60, and then we're going to follow whatever bracketed numbers we find. We're going to follow that to our two-sided P, because that's what we're actually doing here, is we're using a two-sided P. So let me just erase. Let me just erase some of what I drew on here. And what I'm going to do is I'm going to actually try to make this a little bigger so that we can zoom in on this a little bit. It's going to be a little tough, but we'll see if we can get this done. So 3.3, if I look at the row of 60 here, and I'm still on my eraser, sorry. If we look at the row for 60, which is right here, we can try to find 3.3 in this row, or whatever, it comes pretty close. And it looks like somewhere between here and here is 3.3. So 3.2 to 3.4, somewhere in the middle there is 3.3. And so if we follow that down to our two-sided P down here, so we're looking at this, the two-sided P, you can see that the number is somewhere between 0.002 and 0.001, I think that says. So by looking that up, so this is table C, we get somewhere, our p-value is somewhere between 0.001 and 0.002. Now both of those numbers are much less than 0.05, which is what we assumed when we set this whole thing up. If you recall, we assumed a 0.05 level of significance. And both of these numbers are much less than that. So we can actually, just by looking at those two numbers, we can say, they're significantly less than our level of significance, and therefore we can reject our null hypothesis because of that. So, and if you recall, our null hypothesis was that mu is 15 years. So really what we're saying is that this estimate is incorrect. This 15 years, it's not 15 years, it's something else. It could be 12 years, it could be 17 years, but we don't know. But we know it's not 15 because there's evidence that shows that this is incorrect. So that is how you do not only a t-distribution, but a two-sided t-distribution.